In the summer of 2025, astronomers spotted an object crossing through our solar system that they genuinely could not measure with any real precision. And the reason why says something fascinating about the actual limits of what even our most powerful telescopes can do. Not because the object was too far away to see, not because it was hiding. Because the specific combination of its distance, its darkness, and the physics of light itself made pinning down something as basic as its size into one of the harder problems in modern observational astronomy, a problem that remained genuinely unresolved for months, debated openly among specialists and published peer-reviewed papers, rather than quietly settled behind the scenes. This is the real story of 3I Atlas, the third confirmed interstellar object ever detected passing through our solar system, and why, months after its discovery, scientists still could not agree on whether it was smaller than a mountain or larger than a small city. Before going further, it is worth being precise about what this story is not, because the specific framing matters enormously here. This is not a story about an object larger than Jupiter sitting anywhere near Earth's orbit. Nothing like that exists in the data, and nothing like that could exist without being immediately, catastrophically obvious to literally everyone on the planet, visible without a telescope, large enough to disrupt the orbits of nearby planets through its own gravity alone. An event that would dominate global news for the simple reason that it would represent one of the largest astronomical developments in recorded human history. An object the size of Jupiter, roughly 88,000 miles across, drifting anywhere near Earth's orbital distance from the Sun, would visibly distort the orbits of every planet in the inner solar system through gravitational interaction alone, effects that would have been measurable and unmistakable months or years before any such object could plausibly sneak up on anyone. Nothing resembling that scenario appears anywhere in the actual scientific record. What actually happened is smaller in scale, but genuinely more interesting once you understand it. A real, confirmed visitor from another star system, somewhere between the size of a small mountain and a mid-sized asteroid, whose exact dimensions became a genuine point of scientific uncertainty and debate for months after its discovery. The object was first detected on July 1st, 2025, by the NASA-funded Atlas survey, the Asteroid Terrestrial Impact Last Alert System, operating out of a facility in Rio Hurtado, Chile, part of a network specifically designed to scan the sky repeatedly for exactly this kind of moving object. Within days, astronomers confirmed something remarkable about its trajectory. It was moving on a hyperbolic path through the solar system, curved, too sharply to ever have been gravitationally bound to our sun, the same basic mathematical signature that had confirmed the interstellar nature of both objects discovered before it. It had arrived from interstellar space, from the darkness between the stars, and it was passing through on a one-way trip, never to return. That made it only the third confirmed interstellar object ever recorded in the history of human astronomy, following the strange, tumbling Oumuamua in 2017, an object so bizarre that scientists spent years arguing over its true nature before it disappeared from view entirely, and the more conventional interstellar comet Borisov in 2019. Astronomers designated this newest visitor 3I Atlas, the 3I standing simply for Third Interstellar. At its closest approach to the Sun on October 29, 2025, 3I Atlas passed at a distance slightly closer than Mars's own orbit. At no point did it ever come anywhere near Earth's orbit in any meaningful sense, its closest approach to our planet occurring afterward. In December 2025, at a distance NASA explicitly confirmed posed zero threat to Earth, tens of millions of miles away, well outside any range that could plausibly be described as a close encounter, let alone a moment of danger. For most of its passage through the inner solar system, it actually sat closer to Jupiter's orbital distance than to Earth's, a detail worth remembering any time a headline suggests otherwise, and a useful benchmark for understanding just how much distance actually separated this object from our own planet throughout its entire visit. What makes 3I Atlas genuinely interesting is not any imagined proximity to Earth, but the very real difficulty scientists faced in determining something as basic as how big it actually is. To understand why that difficulty exists at all, you first need to understand how astronomers typically measure the size of a distant object, like a comet or an asteroid, because the method is far less direct than most people assume. Telescopes do not photograph small, distant objects like 3I Atlas the way a camera photographs a nearby object, resolving its actual physical shape and edges with any clarity. At the distances involved, even the most powerful telescope in the world sees an object like this as an unresolved point of light, a single glowing dot with no discernible shapes at all, regardless of whether the true object underneath happens to be perfectly round, oddly shaped, or tumbling unpredictably through space, the same basic limitation that affects how we observe distant asteroids, comets, and even some smaller moons throughout the solar system. Determining a physical size from that single point of light requires inference, not direct measurement, And that inference depends heavily on assumptions that are much harder to verify for an interstellar visitor than for an object native to our own solar system. The first major size estimate for 3I Atlas came from the Hubble Space Telescope, which observed the object on August 20th, 2025, roughly 7 weeks after its discovery, using its exceptional resolving power to capture the sharpest available image of the object during that early window of its passage through the solar system. Working from that data, astronomers calculated a nucleus diameter somewhere between 440 meters and 6 kilometers. Sit with the width of that range for a moment, because it is genuinely enormous by the standards of modern astronomy, spanning more than a factor of 12 between its lowest and highest bounds, a level of uncertainty that would be considered a significant scientific problem in almost any other context. For comparison, in size terms, the smaller estimate is a little wider than the island of Manhattan is long, while the larger estimate would make the object bigger than most asteroids ever tracked by any survey, a range so wide that it left researchers with two dramatically different pictures of what they were actually looking at, everything from a modestly sized comet nucleus to something approaching the scale of a small, irregularly shaped moon. That uncertainty exists because of a specific, well-understood limitation baked into how brightness-based size estimates actually work. When a telescope measures how much light is coming from a distant object like 3I Atlas, that brightness depends on two things multiplied together: the object's actual physical size and its albedo, a measure of how much of the sunlight hitting its surface actually gets reflected back toward the observer rather than absorbed. A large, dark object and a small, highly reflective object can produce nearly identical brightness readings from Earth, because the extra light-reflecting surface area of the larger object gets canceled out by its lower reflectivity, while the smaller object's higher reflectivity compensates for its smaller surface area, a genuine mathematical ambiguity baked directly into the underlying physics of the measurement itself, not simply a matter of needing a better instrument or a longer exposure time. Without an independent way to measure albedo directly, astronomers are left estimating it based on typical values observed in other, better-studied comets and asteroids, a reasonable approach for objects that formed inside our own solar system, where decades of prior observations, including direct spacecraft visits to several comets and asteroids, provide a solid baseline for what albedo values are actually common across different types of icy and rocky bodies. For a genuinely interstellar object, formed around an entirely different star, under entirely different conditions, billions of years before our own solar system even existed, that baseline becomes far shakier. There is no strong reason to assume an object built from the raw material of another star system would necessarily share the same surface reflectivity as the comets and asteroids native to our own, since the specific chemistry and formation conditions of a completely different star system could plausibly have produced surface material with meaningfully different optical properties than anything we have direct experience studying. Compounding the problem further, 3I Atlas was actively venting gas and dust throughout the period. Astronomers were trying to measure it, a normal and expected behavior for any comet warming as it approaches the sun, but a significant complication for anyone trying to isolate the brightness of the solid, icy nucleus underneath. The glowing cloud of gas and dust surrounding a comet's nucleus, called the coma, can itself reflect and scatter a meaningful amount of sunlight, adding extra brightness to the overall signal that has nothing to do with the size of the solid body hidden inside it. Untangling exactly how much of the light Hubble and other telescopes were recording came from the actual nucleus, versus how much came from the surrounding cloud of venting material, added yet another significant source of uncertainty to the final size calculation, one that different research teams, using different assumptions about the coma's own contribution, resolved in somewhat different ways. Different observational techniques, applied at different points during the object's passage through the solar system, produced their own separate estimates, each with its own specific set of assumptions and limitations. Thermal infrared observations, which measure the heat radiating directly off an object's surface rather than the sunlight it reflects, offer one alternative path to estimating size, since thermal emission depends primarily on an object's actual surface area and temperature rather than on its reflectivity, sidestepping the albedo problem that complicates purely optical brightness measurements. But thermal measurements carry their own complications for an active, gas-venting object like 3I Atlas, since the surrounding coma can also glow in infrared wavelengths, once again mixing signal from the nucleus with signal from the material actively escaping its surface. Different teams, applying different combinations of these techniques at different points during 3I Atlas's several-month passage through the inner solar system, arrived at estimates that shifted somewhat over time as the object's distance, activity level, and observing geometry all changed. A moving target in the most literal sense, studied by an object that was itself actively changing, while astronomers tried to pin down its basic physical dimensions. There's a genuinely instructive lesson buried in all of this uncertainty, one that reaches well beyond 3I Atlas specifically. For decades, science communication has often treated a telescope's ability to detect a distant object as roughly equivalent to fully understanding it, a single clean number reported confidently in a headline, when the underlying reality is frequently far messier and far more uncertain than that clean number suggests. Detecting 3i Atlas was, in a real sense, the easy part, a matter of a survey telescope flagging a moving point of light and confirming its unusual trajectory. Determining its actual physical size turned out to be a genuinely difficult scientific problem, one that involved competing estimates, ongoing debate among specialists, and a level of honest, acknowledged uncertainty that rarely makes it into the more sensationalized corners of space content online, where a wide, honest range like 440 meters to 5. 6 kilometers gets quietly collapsed into whichever single number sounds most dramatic, or in some cases, invented outright as something that never appeared in any actual scientific paper at all. That honest uncertainty did not stop scientists from learning an enormous amount about 3i Atlas through other means, methods that did not depend on nailing down its precise physical size at all. The James Webb Space Telescope studied the object's chemistry in exhaustive detail across 2 separate observing campaigns, in August and December of 2025, finding an unusually high ratio of carbon dioxide to water in its coma, among the highest ever recorded in any comet, a chemical signature suggesting this object formed under conditions radically different from anything present in our own solar system, and achieving the first direct detection of methane gas ever recorded in any interstellar object, an entirely new class of finding regardless of how large or small the underlying nucleus actually turned out to be. Separate analysis of the ratio between 2 specific carbon isotopes in the comet's gas, carbon-12 and carbon-13, suggested the object had formed somewhere between 10 and 12 billion years ago, making it quite possibly the oldest comet ever directly studied by humanity, a fragment of a star system that existed in the very early history of the Milky Way, long before our own sun ever formed, older than our entire solar system by a margin of several billion years. None of that chemistry, or that staggering estimated age, actually depends on resolving the exact size debate. The most scientifically significant findings about 3i Atlas turned out to have very little to do with the specific number astronomers eventually settled on for its diameter, a reminder that a single, precise measurement is not always the most important piece of information a scientific investigation actually produces, and that genuine scientific value can come from an object, even while some of its most basic physical properties remain honestly, openly uncertain. It is also worth understanding why this specific kind of size uncertainty tends to resolve itself so slowly, and sometimes not at all, for objects passing through on a one-way interstellar trajectory. For an ordinary asteroid orbiting within our own solar system, astronomers can typically wait for repeated observations across multiple years, sometimes decades, gradually refining a size estimate. As the object returns to view again and again from different angles under different lighting conditions, allowing researchers to slowly narrow down the true albedo and eliminate competing explanations, one observation at a time. An interstellar object like 3i Atlas offers no such luxury. It passes through the inner solar system once, is observed as intensively as possible during that single limited window, and then departs permanently, accelerating back out into interstellar space, never to return, crossing the orbit of Jupiter in March of this year on its way back out of the solar system for good. Whatever size estimate the scientific community eventually settles on will likely remain the final word on the subject, refined perhaps by continued analysis of the existing archived data, but never improved upon by fresh observations, because there will never be a second opportunity to look again. That permanence is, in its own way, part of what makes this kind of scientific uncertainty worth sitting with, rather than glossing over. Every interstellar object humanity has confirmed so far, Oumuamua in 2017, Borisov in 2019, and 3i Atlas in 2025, has passed through our solar system exactly once, observed intensively for a matter of months before disappearing permanently back into the depths of interstellar space. Each one has left behind a body of data that is, in a very real sense, finished, complete in whatever form it happened to be captured during that single, narrow window, with no possibility of a follow-up observation ever correcting or refining it further. Getting the most out of that limited window, using every available telescope, every available technique, and being honest about exactly where the resulting uncertainty actually lies, matters enormously precisely, because there will never be a second chance with this particular object. Scientists are continuing to analyze the full body of data collected on 3i Atlas as it recedes farther from the Sun, work that will likely continue for years, refining estimates of its size, its composition, and its exact age, using increasingly sophisticated modeling techniques applied to data that has already been fully collected and archived. It is entirely possible that the size estimate will narrow considerably as that analysis continues, converging on a number closer to one end of the original range than the other. It is equally possible that meaningful uncertainty will persist indefinitely and permanent asterisk attached to one of the most scientifically significant objects ever to pass through our solar system, not because anyone failed to do their job carefully, but because some questions, given the physics actually involved, simply resist being answered with total precision, no matter how good the available instruments happen to be. If this is the kind of story you want more of, subscribe, and let me know in the comments whether you think 3i Atlas turns out to be closer to the small end of that size range or the large one.